Alright, hi y'all. Today we're going to be going over the Smith chart problem from, I think, like 2021, from exam 2. Yeah, hopefully this time my mic doesn't die in the middle of the video, because, yeah, I guess now I have to do this over again. So, starting this problem, Smith charts themselves, I mean, just looking at it, it's a little bit of a mess. Like, what is even going on? But let's try and pick apart this problem first. So what do we notice whenever we read this problem? We see that we have a characteristic impedance. We have a regular coax of 50 ohms. It says the cable may assume to be lossless. So what does that mean for us? Well, that means the dielectric wavelength is equal to the guided wavelength. It'll become more important later on. And it says and it's filled with a dielectric material having an unknown relative permittivity. Unknown relative permittivity, that's epsilon r, which in the first problem here we had to solve for. Okay, but we're getting ahead of ourselves. Let's try and keep, reading this problem. It says the line is operating at 1 gigahertz, which is the frequency. Now it says on the line, the magnitude of the voltage is maximum at a distance of 3 centimeters from the load. Okay, so before we do this, when we start seeing lengths and max and min voltages, our mind should go straight towards Smith charts. But not only Smith charts, but our voltage standing wave ratio chart. So what is this voltage standing wave ratio chart? Or, your just regular SWR chart. Well, what this is this is a chart that tells us where and when, maybe not where and when, but where specifically our voltage max and mins will occur with respect to the wavelength, the wavelength here. So what do we know? Well, we know the max occurs at 3 volts. And our min voltage is 1 volt. But where do they occur? When exactly does this occur? Well, the voltage max happens at a distance of 3 centimeters from the load. So we have these Vmax and Vmax right here. Well, where's the load? Well, the load is this value, or this position. You're starting at the load and your wave is going to the right. I guess it should be going to the left, but we're portraying it to be towards the right, towards the left, sorry. And we know over here is the source, or our generator. And what did we say? It's 3 centimeters from the load. So if we know the load is this line and we know 3 centimeters away is this, we know the distance from here to here is 3 centimeters. Hopefully you're seeing exactly what this is. And now it's saying it's 3 volts, which we already plotted. And we know the min is 1 volt, and it's a distance from the max point, not from the load now. We're at the distance from the max point, which is here. I'll draw this here to here is what, 5.17 centimeters. All right, so now we've created our SWR chart, or our little graph here, which will make it very easy for us to create the Smith chart. Now, we have to find out what the relative permittivity is. Now, this is just a set of equations that we have to use, and it's actually given in the formula sheet. So I won't bother, showing these formulas. I'll write them down. One of the formulas is that lambda 0, which this should already be known, is equal to the speed of light divided by the frequency that this line is operating at. What else do we know? Well, we know lambda d is equal to, this one might be a little more obscure. This one you'll definitely have to look at the formula sheet. It's equal to the lambda 0 divided by the epsilon r. What do we know? Well, epsilon r, that's what we're looking for. We know lambda 0 because this is given to us, but lambda d, that's something new. That's not given to us straight out. So we have to find it. But what is lambda d? Well, lambda d is the wavelength, the guided wavelength, the entire wavelength. So we have to figure out what that is. Well, looking back here, this graph this chart here will tell us exactly what that is. Something that you do have to know is the distance from the max, the voltage max to the voltage min, is lambda d over 4. So what we can do, this lambda d over 4, because again, this is another max and min, And then what? This lambda d over 4. And then, well, we have this little distance here, and we have this little distance here. So this is going to be, these two, this one here and this one here, should add up to lambda d over 4. Okay. Well, what is lambda d? Well, we can use the fact that we know what lambda d over 4 is. We know we know lambda d over 4 is equal to what? 5.17 centimeters. And this is given to us in the problem. It says the distance from the max voltage to the minimum voltage is 5.17 centimeters. You have to know right away, even if it tells you to not use the Smith chart, draw this out because it will help you understand how the wave is acting, what the properties of this wave are, how far up it's going, how far down it's going in voltage, how far the wavelength is, how does that correspond with frequency. Okay, anyways, we know then that lambda d is equal to 4 times 5.17, which is 20.68 centimeters. Yeah, so now we know lambda d is, we know what lambda d is, we can solve for epsilon r, that's an easy problem, that's algebra. We know epsilon r is then lambda 0 over lambda d squared. Lambda 0 is c over f. Well, we know c is 3 times 10 to the 8th speed of light divided by 1 gigahertz, which is 1 times 10 to the 9th hertz. Again, 1 over seconds, so we have meters over seconds, or I guess it's seconds over meters. Whatever, the seconds cancel. So we know that, lambda 0 is this value, and we know lambda d now is 20.68. Well, what do we have here? We have 0.3 over 20.68. I forgot something. This squared is important. This squared here is very important also. And let me make sure if that's right. So yes, that should be right. But remember, this is in meters and this is in centimeters. So this needs to be 20.68 times 100 or times 10 squared. Okay, and what we now get is that this is equal to, wait, hold on, centimeters to meters. You get smaller, so this should be -2. Okay, so you get 2.104 as your voltage standing wave ratio. And let me make sure that's right before I say it's not. So this should be 0.2068 times itself. Yes, that's right. Okay. Yes. All right, so now we have this epsilon r. Perfect. We found part A. We get, what, 15 points. Perfect. Nice. Now, what do we need to do? Well, we need to use the Smith chart to find the unknown load impedance. So the unknown load impedance is what? ZL. But Smith charts don't use load impedance. They use normalized values. So what is the normalized load impedance? That's what we're looking for when we solve for the Smith chart. Or if it asks you to find the admittance, the load admittance, we would first find the normalized load admittance on the Smith chart. So now we know that the normalized load impedance is, well, we don't really know what that is. We need to solve for that on the Smith chart. Well, how do we get normalized load? Or maybe not normalized, but regular load. Well, regular load is equal to the normalized load impedance times the Z0, which we said was 50 ohms. So that's the characteristic impedance. Okay, anyways, let's get to the Smith chart. That's pretty much what everyone here is for. The Smith chart here, there's two things we have to know, and this is why I make this graph. We have to know where the Vmax and Vmin occur. On the Smith chart, on this right side, we have Vmax here on the very right and Vmin here on the very left. Okay, well, what else do we know? Well, it's very important that we know the distance it takes to get from Vmin to Vmax. And this, of course, tells us, I've said this before, the distance from the Vmin to the Vmax, from Vmin to Vmax, is 0.25 lambda d, a quarter of a wavelength. Okay, so if we know the distance from Vmax to Vmin is a quarter wavelength, And we know the distance from Vmax to load is, that's unknown, right? We need to find that. Huh. Well, how are we going to find that? Sorry, I went on a little tangent about Vmin, Vmax, and 0.25. That doesn't happen. That isn't really important until like right after this step. The first thing you would need to do here is find out your standing wave ratio circle. Well, what is our standing wave ratio, or VSWR, sorry, a voltage standing wave ratio? That's our Vmax, the magnitude of our Vmax divided by the magnitude of our Vmin. Well, what is Vmax and what is Vmin? We have 3 as our Vmax and 1 is our Vmin, right? We have 3 volts here and 1 volt here. So our VSWR is going to be 3. What is VSWR, though, in terms of a Smith chart? VSWR is the circle you create around the center with the radius of whatever your VSWR is. Of course, this is going to be very bad. Wow, I didn't even make a circle. That's crazy. It's going to be really bad. This is, I encourage y'all to get a compass. This will help a lot when you're doing it on paper. Already looking at this is not going to give you the right answer because this isn't close enough. That's not a circle though, so yeah, this is going to probably not give us the exact answer, by the way. But I'm just showing y'all the process. I'm kind of sucks that my circles are terrible, but I digress. This is a good enough circle. It is what it is. So this is our VSWR circle, VSWR, and this is equal to 3. You notice I started at 3 and started making that circle. That's what you need to do. If you have a voltage standing wave ratio of, I don't know, 0.5, maybe not 0.5. Let's say it's, because that would mean Vmin is greater than Vmax. That wouldn't make any sense. Let's say Vmax and Vmin, it's 2 to 1. So you have a circle. What I would do is I would start at this point and just make a circle like this with your compass. Okay, so anyways, that's our VSWR circle. We need to know this because wherever our line intersects this VSWR circle, that is our normalized load impedance. I'll show you what that means. What this means is we need to figure out the distance in wavelength from the load to the either Vmin or Vmax. Now, it already tells us that it's 3 centimeters. The load is 3 centimeters from the max point. So it might be a little easier to use this. The way you would do this is the distance from the max voltage is equal to the distance from the max voltage in centimeters, and of course this is in wavelengths, by the way. This is the distance from the max point, a voltage point, in centimeters, which is what, 3 centimeters, divided by the entire wavelength, which, what did we have? 20.68 centimeters. You notice this gives us a ratio of wavelengths, and this gives us 0.145 lambda d. Now, this is lambda d because this one entire thing, this one wavelength is lambda d. But we only want a portion of that. We only want to find the distance from the max point to the load. So we want to find only 0.145 lambda d. Okay, but like, what does that tell us? What this tells us is it from the max, from this point here, we are 0.145 going towards the generator or away from the load. Or sorry, we're going towards the load. So we're going from Vmax here to the load, right? It's 0.145 lambda d. So starting at this point, which is what? This is lambda d over 4 of quarter wavelength, back towards the load. Back towards the load is counterclockwise. Okay, so that means we're going 0.145 back towards the load, which is a 0.25 lambda d minus 0.145 lambda d. We get 0.105 lambda d. So this is the distance from the max point this 0.145 lambda d. So really you don't have to do this subtraction. You really just need to know the distance from the load, from the max voltage, which will be 0.145 away. Or you could do 0.25 minus 0.145, makes it a little easier for yourself because now you can start at this point. And now 0.105 is here, sorry, is going to be 0.105. So past 0.1, it's going to be about here. Okay, so now we make a circle, or not make a circle, we just make a line to the center here. We put the center there. It's a little off, but it is what it is. Here. Okay, so now what we do is we find our normalized load impedance. So we can draw lines here, which is about 0.6. And we notice this one here is about 0.58. So we have the normalized load impedance. And of course, this isn't exact because obviously my circle is off and then this thing isn't even connected. If you do that during the exam, I think you'll be totally fine. As long as you can show you have the process down, you'll be totally fine in heat grades. Sometimes pretty tough, but if you have the process down, there's no way you get, minus 15, minus 20 for a wrong answer. So now you have 0.6 plus 0.57. We said 0.57. And remember, up here in the positive quadrant is what? This is inductive. So we have positive reactance. Down here is negative, it's capacitive. So we have a negative reactance, and now we want to find the load impedance. Remember how we did that? Load impedance is 50, or your characteristic impedance, times your normalized load impedance, which now we have 50 times 0.6 plus 50 times 0.7. So 50 times 0.6, so we have 30 plus 0.57 times 50, 28.5. All right. There we go. So we've solved for load impedance. And notice how we used this VSWR for literally everything. It's very important you understand how to make this little graph here and import, or I guess export, all of our information into the Smith chart, because this is basically the Smith chart, just in wave form. Here it's a better visualization of your load impedance and being able to solve for load impedance easier. But anyways, hopefully this helped y'all. I'll even put this is 0.105 lambda d, and then this part here is what, 0.145 lambda d. Maybe this will clear up some confusion about how I got the distances. Notice how the addition of 0.105 and 0.145 is 0.25, a quarter of a wavelength. So yeah, that's how you do this. I'll definitely be making more videos over Smith charts, especially open stubs and short circuit stubs, and maybe quarter wave transformers, because not only is that going to be on the exam, but also that is on our project. So if you haven't started that, make sure to, preferably, maybe after the exam. But anyways, yeah, hopefully this has helped y'all. But yeah, thank you for joining.